Professor Belfrost's computer science class is back!
Hi, welcome back. And here's Professor Belfrost's class on computer science. And today we are going to explore another concept on computer science, continue our last lesson. And if we are already ready for today's episode, then let's go. Good. So let's see. Let's continue from our last discussion. So we have done with the review on Boolean algebra and number system, and we'll continue now to explain about part of computers component, which is the ALU part. Okay, so ALU is very important, and the basics is the Boolean algebra and the logic circuit and the number system that you have we have learned so far. And okay, let's see. There are some points that we will learn. Okay, so we have ALU, we have integer representation, we have integer arithmetic, floating point representation, floating point arithmetic, and some of them we have covered in the previous videos. So I'll not discuss about that again, but let's review a little. Let's see if this book can give us another insight. Okay, so first thing that we need to really understand about is that the ALU is that part of the computer that actually performs the arithmetic logic operation as its name suggests. Okay, so an ALU, okay, and indeed all electronic components in a computer are based on the use of simple digital logic devices that can store binary digits and perform simple Boolean logic operations. And here's the interconnection, ALU input and output. Okay, so the inputs are control unit and registers, while the outputs are flags and registers. Okay, so let me check if okay the video is still on. Okay, so integer representation, we have discussed about this, right? Okay, so we have what called radix point, okay, which is yeah, a period between. Okay, so it says that in the binary number system, arbitrary numbers can be represented with just the digits 0 and 1, the minus sign, and the period or radix point. Yeah, actually we have discussed about this before, also how to convert the binary to decimal, decimal to binary, both integer, also including the fraction part. Actually we have discussed about this, and this is just quick review. Okay. Okay, so sign magnitude, we also have discussed it using two's complement. We can find the sign magnitude, and you need to notice that the most significant bit part here. Okay, so the last digit on the most significant bit part here is that for positive number it is 0, and for negative, I'm sorry, it's hard for me to highlight the text, it is 1. Okay, so the general case is as shown. So I want you to pay attention to the note 91. Okay, so yeah, actually here is a drawback if we stick to this uh, rule. Okay, because it means that we have two different representation for 0, right? We can represent 0 as positive and also negative, and this is inconvenient. So yeah, here is what we have discussed, choose complement representation. So yeah, let's see how this book reviews it. Okay, so this is the step, okay, on characters of the choose complement representation and arithmetic. Okay, so yeah, this is the summary for you. I really want you to read it. Okay, so we can express a number with n bits from minus with a value from minus 2 raised to the power of n minus 1 through positive 2 raised to the power n minus 1 minus 1. Okay, and there only one representation for 0. Okay, negation, we just need to take 2's complement, which is to complement each of the bits corresponding to a positive number and then add 1 to the resulting bit. Okay, expansion, overflow we haven't discussed actually. We will discuss in this lesson. Okay, so if two numbers with the same sign, with both positive or both negative are added, then overflow occurs if and only if the result has the opposite sign. This is a prior notice for you that you need to understand about. Okay, so subtraction rule also is very easy. We have discussed in previous episodes. Okay, let's see if there's up. Okay, so this is how we represent the 2's complement using such formula. I think it's not very convenient to memorize a long formula. That's why I have taken other resources when I giving a course on 2's complement and how to do another operation. Okay, because this book is not very convenient for you. Okay, so there are quite many things. Let's see. Okay, so this is how we do complement. All of these are equations. So I really want to skip and take just the important things. Let's see. Okay, negation. So with negation, 2's complement notation that the negation of an integer can be formed with the following rules. So you take the Boolean complement of each bit of the integer and then treating the result as an unsigned binary integer. Okay, that is the 2's complement rule actually. Okay. Okay, so it says that as expected, the negative of the negative of that number, the negative of the negative of that number itself is the positive. So actually, positive to negative, negative back to positive is okay. It's the same thing. Okay. Okay. So here's the first consider a equals 0. In that case, for bit 8, an 8-bit representation that is 0 is 0 0 0, and if we complement it we get 1 8 bits of 1, and if we add 1 they become overflow 1. Okay, but the quotient, the result is 0, so there is a carry out of the most significant bit which is ignored, and the result is that negation of 0 as it should be. Okay, but how about the minus 1 to 8, which is the largest negative number possible? Okay, because for 8-bit number is from minus 1 to 8 to 1 to 7. Okay, so if we complement it, it also become minus 128, which is we get back the same number, and this is unavoidable. This is an anomaly. Okay, so the number of different bit patterns in n bit was into to n, which is an even number. Okay, so yeah, let's see. There's some case, okay, exceptional case that the rule cannot doesn't apply well. Okay, so here's the important part. Okay, I've been seeking for this. Okay, so on any addition that the result may be larger than can be held, then it is called an overflow. Okay, so when the overflow occurs, that the LU must signal this fact so that no attempt is made to use the result. Okay, so there must be a warning, right? Okay, so if two numbers are added and they are both positive or both negative, the overflow has occurred if and only if that the result has the opposite sign. So please pay attention to this table. This table show you when the addition or the subtraction showing the overflow signal. Okay, so if we have minus 7 and 5 with a minus 2, it's okay. Okay, it's minus 4 4, it's 0, it's okay. Okay, 3 4 7 minus 4 minus 1 minus 5, but minus 7 minus 6, do you understand what actually this means? This actually, it says this. How can I say? Oh yeah, this. Uh, the result has the opposite sign. Okay, when both positive and both negative, then the overflow occurs if and only if the result has the opposite sign. Let's see. Okay, with the different sign of the uh, things that we want to add or subtract, we cannot um, decide. We cannot determine if there occurs any overflow or not. But for example, for C, D, E, and F, we can. Okay. So for C, let's see, we add two positive numbers. Okay. So with positive number, it start with 0, right? And the result also 0, the MSB. Okay. So it is okay. How about with this minus 1 minus 1? It start with 1, 1, and the results also 1. Okay, so it's okay. There's no problem with it. But for this one, you see, 0 is 0, but the result is 1. So there must be a overflow. How about this? 1, 1, and the result is 0. Okay, please pay attention. This is not, we are discussing about the result, okay, not the overflow. Okay, we are only considering how many bits as the uh, one that is the operation have the maximum number. For example, for this, we add 4-bit number with another 4-bit number. It means that we are dealing with 4 bits. So if there are the 5th bit, we ignore that. We only take the MSB from the 4 bits result. Okay, so it's so different kind of sign. It means there has been overflow. Also for subtraction, there's a subtraction rule that you need to pay attention to. So to subtract one number, subtrahend from another minuend, take the two's complement negation of the subtrahend and add it into the minuend. Actually, we have covered it, right? But here what I want to um, emphasize about is when we come to the overflow situation. Okay, let's see. We add two numbers. Okay, so minus 6 and minus 5, a minus 4 I mean, and it shows something like this. Yeah, actually this is just the reverse operation. I want you to find the way to express overflow by yourself. You see, so subtraction of positive number is spin to left, addition of the positive number is spin to right. Also addition of positive number right, this is a left. Okay, so this is the geometric depiction in a circle form. And here's the block diagram of hardware for addition and subtraction. So we have two register, B register, A register. B register is fed to the complementer, complementing to the SW. Also B register going directly to the SW, and the SW do an operation and pass it to adder, A register to adder. Then we have overflow, okay, OF overflow bit. As we switch is actually, I think this is a like multiplexer, okay, and it's fed back, okay. Multiplication we also have done with this in our previous episodes, and I want you to take example of how to do this in this book. And here's how the configuration of multiplier works in uh, in Isaac computer. So here's a flow chart how to do unsigned binary multiplication by computer. So we have yeah, I think this is counter adder. I think again multiplier count. Yeah, I really understand what is this shorthand of the CA things, but yeah, here's the flow chart. Maybe you can pay attention to. Oh, this is all just register. We have A register, C register. Yeah, this is all register, just register. Okay. And here's how to do the multiplication by computer. Just complement multiplication. Okay. I will just not discuss it into depth because actually I want to Okay, arithmetic shift. Oh, shift. We have also covered about shift register, right? In our previous episodes. Yeah, that's great. Okay, actually, to do multiplication in binary, actually, it's the same way we do multiplication using decimals, right? Okay, we multiply one by one. Okay, for example, like this. Maybe you ask why there are three rows, but actually, it is self-explanatory. Okay, we do arithmetic shift. That is the answer. Okay. Okay, here's the step that you maybe want to pay attention to. Division also. Here's how to do division. Actually, I explained it before how to do. Here's how computer do the division. Okay, let's see if we can skip it. Okay, also here's about floating point representation. I've also covered in a special episode, right? Okay, so here is the representation of floating point representation. We have sign, significant, and exponent. Maybe significant term, I use mantissa, right, in the last episode. Okay, yeah, that's the same thing. B is stand for base. Okay, okay, floating point is expressed as zone. Actually, this is the same thing that I've discussed before. Okay, so okay, here's the point. So 5 digits on the number line I'm not including in this range, which is negative overflow, negative underflow, 0, positive underflow, positive overflow. Okay, so you maybe need to understand by yourself how this thing happen. Here's the figure. I really don't want to take too long to cover this because this is all a little complex and this is all just calculation by calculation, operation by operation. I don't want to discuss the programming things with you. So let's see if I can skip. I don't mean that this is not important. I want you to review it by yourself. Okay. Subtract change of y x equals 0. Yeah, this is quite complex flow chart for you to review by yourself. Maybe I should skip to the next chapter. It seems like the same thing here. Okay, just start discussing about instruction sets. Maybe this is the best way. Okay, let's see the key points first. So the essential elements of a computer instruction are the opcode. They would specify the operation to be performed, the source and destination of reference, which specify the input and output location for the operation, and a next instruction reference, which is usually implicit. Opcodes specify operation in one of the following general category, which is arithmetic logic, movement of data, register movement of data, or two. Oh, yes. So this is the first one, arithmetic logic, movement of data, I/O, and control. Actually, there are four things, right? Oops, it's quite difficult to highlight this. I've discussed this at I think the third or the fourth video. Okay. So operand references specify register or memory location of operand data. Common architecture feature is processed in the stack. Oh, maybe this is what I want to explain a lot. And yeah, there are many kind of endian system that we will discuss later. This is a very important concept actually. I'll maybe pay more attention to explain that to you. Okay, so let's see. So the operation of a processor is determined by the instruction it executes, referred to as machine instruction or computer instructions. And a collection of different instructions that the processor can execute is referred to the processor instruction set. So here's the instruction cycle state diagram. Maybe we have encountered this before, but let's just review it again. So yeah, this is how it works. It flows like this. So let's see here. Here are four elements of machine instruction that have been summarized before. Okay, it's quite hard to use this. Okay. So first is operation code, which specify the operation to be performed. Okay, then source operand reference, that the operation may involve one or more source operand. Okay, and result operand reference, that the operation may produce a result. And next instruction reference, which tells the processor where to fetch the next instruction after the execution of this instruction is complete. And this is important thing. The address of the next instruction to be fetched could be either a real address or a virtual address depending on the architecture. I will later explain many types of address on the next chapter or on the next two chapters. Maybe I really memorize the structure of this book. Okay, but we'll explain there later. Okay, and here's the important thing too: source and result operand can be in one of four areas. The first one is in main or virtual memory. The second is in processor register. The third is immediate. The fourth is IO device. So within the computer, its instruction is represented by a sequence of bits, and the instruction is divided into fields corresponding to the constituent element of the instruction. So if it is difficult for both the programmer and the reader of textbook to deal with binary representative of machine instruction, thus maybe the common practice to use is symbolic representation of machine instruction. So we'll dealing with symbolic representation from now on. So here's the symbolic representation meant on the previous paragraph. So opcodes are represented by abbreviation. This is called mnemonics. For example, add for add, sub for subtract operation, mul for multiply, diff for divide, load for load data from memory, store for store data from memory. And operands are also represented symbolically. Okay, for example, we have add r comma y means that add the value contained in data location y to the content of register r. Okay. Next instruction type. Okay, so here's the main thing. We can categorize instruction type as follow. So there are four: data processing, data storage, data movement, and control. So arithmetic instruction provide computational capabilities for processing numerical data. Logic or Boolean instruction operate on the bits of a word as bits rather than as numbers. Thus, they provide capabilities for processing any other type of data the user may wish to employ. There must be memory instruction for moving data between memory and the registers. I/O instruction needed to transfer program data into memory and result of computations back out to the users. Then test instruction are used to test the value of the data or research of computer. Branch instruction are then used to branch different set of instructions depending on the decision made. Okay, now we enter a new topic: number of addresses. So here is the critical point. What is the maximum number of addresses one might need in instruction? Okay, evidently, arithmetic and logic instruction will require the most operands. So virtually all arithmetic logic operations are either unary or binary. So we will need a maximum of two addresses to reference operands, and the result of an operation must be stored, such as a third address, which defines the destination operand. And finally, after the completion, the next instruction must be fetched and its address is needed. And this suggests we need four address reference to source operands and one destination operand and the address of the next instruction. Okay, but in most architecture, most instruction have one, two, or three operand addresses, with the address of the next instruction being implicit. This is the key point, which is obtained from the PC program counter. And let's see if we have example with this. This is the instruction. address instructions, two address instruction, three address instruction, which is the most common one. This is how to execute y equals this operation. Okay, so we have what called a accumulator register. So the accumulator contains one of the operands and is used to store result. Okay, this is quite important. Let's see if I can highlight the most important one for you. Okay, zero address instruction applicable to special memory organization called stack. So stack is a LIFO. We enter a new discussion. Okay, we have LIFO, FIFO, philo, something like that. We'll discuss it later. Okay, so last in first out set of locations. The stack is in a known locations and often at least the top two elements are in processor registers. Okay, we'll describe it later. Okay. Let's see. I will skip most of these because actually they are quite long. Okay, so instruction set design is quite interesting but also quite complex. So the most important of the fundamental design issues includes operation repertoire, data types, instruction format, register, and addressing. Okay, so yeah, let's see. Okay, let's skip the explanation. I think this have the dedicated section to explain about that. Now entering the second subchapter, which is the types on operands. This is the second big topic on this chapter. So machine instruction operate on data. This is very clear. And the most important general categories are addresses, numbers, characters, and logical data. Let's see one by one. Numbers. Okay, so all machine languages include numeric data types, even a non-numeric data processing. Even in non-numeric data processing, there's a need for numbers to access counters, field widths, and so forth. This is important. I will highlight it. Okay, so actually there is a distinction between numbers or used in ordinary mathematics and numbers stored in computer. Okay, first there is a limit or magnitude of number representable on a machine, and second, in the case of floating point number, a limit to the precision. We'll see why this is later. Okay, so there are three types of numerical data. The first one is binary integer, binary floating, and decimal. This is the most common one. Okay, and also we have this thing for application in which there is a great deal of I/O and comparatively little simple computation, that is preferable to store and operate on the numbers in decimal form, and this is called packed decimal. Okay, so here's the explanation. I want you to read it by yourself. The next type is characters. So a common form of data is text or character strings, and this actually stored using binary data too, actually. Okay, so we have what called IRA, International Reference Alphabet, American Standard Code for Information Interchange, and each character in this code is represented by a unique 7-bit pattern or 128 different characters. Okay, also another code used to encode character is extended binary coded decimal interchange code, okay, for IBM mainframes. I'll not enter it to a great detail, but yeah, this is quite important for you to know. Next, logical data. So normally each word or other addressable unit is treated as a single unit of data is something useful to consider and beginning as consists of n one bit items of data, and this is considered to be a logical data. Okay, so it can take on only the value of one, of true, and zero, of false. Okay, actually, that is the important thing from this, and let's enter a little into the Intel x86 and ARM data types. Okay, with the x86, we have 8 byte, 16 word, 32 double word, 64 quad word, and 128 double quad word bits in length. And here's the data types that using x86 architecture. I want you to read it by yourself. Okay, so here's the data types. And here's the performance. Oh, we still have the, the explanation. Okay, that is for x86, and now we have ARM. For ARM, we have 8 byte, 16 half word, 32 word bits in length. And we have Indian subword. Now we are entering next topic, which is types of operation. So there are actually seven types of operation: data transfer, arithmetical, logical, conversion, I/O, system control, and transfer of control. But I think I will leave this for the next episode. We'll discuss from here. Okay, that's good for today, I think. So yeah, here's for you inspiration. So they never die who have future in them. This is by Meridel Leswa. So thank you for today. And that's all our lesson for today. Thanks for watching. And here's your to-do list. So please subscribe, give a like, comment, and share this video to your friend. I'll be back on every Monday on the same class in computer science. And don't forget to visit our website at https://science.com. Keep watching and be thoughtful. Goodbye. See you on the next episode.